Good morning, I'm Hogan Chen, and this talk is about the study of Linux kernel vulnerabilities. We'll talk about the effectiveness of some state-of-the-art defenses and some possible open problems. So why do we study kernel bugs? This is because the operating system kernel is the trusted tooling base for many systems. And much work has gone into mitigating the effects of kernel vulnerabilities, but kernel bugs and exploits are still prevalent in the kernel, and especially in Linux. So the purpose of this study is to inform the research community about the possible interesting directions of kernel security studies in the future. So there are three contributions of this work, and we also outline our talk. First, we studied 141 vulnerabilities from the CVE list since January 2010 to March 2011. We classified them and studied their distribution in the kernel source code. And second, we studied 9 existing tools that try to prevent these vulnerabilities, and found that these tools only address a small subset of these vulnerabilities. And third, we found that there are some type of vulnerabilities like semantic bugs and DOS attacks that are not addressed by any of these tools, and we think they may be interesting problems for future research. Okay, before we start, we first define 3 terms. There are vulnerability, exploit, and impact. Vulnerability means the programming mistake that the kernel developers made in the source code. And exploits is an attack that the adversary mounted to take advantage of the vulnerability. And the impact means the direct consequence of the exploit. So this table summarizes the distribution of vulnerabilities versus the impact of possible exploits. Here, the row shows the vulnerabilities, and the columns shows the impacts. And now let's see explain each column first. Memory corruption means that a buggy code could overwrite memory locations that it's not supposed to control, like overwriting function pointers, frame pointers, or even arbitrary memory locations. And policy violation means the attacker could bypass the permission checks for some high-level security policies, and like change a file's permission without being the owner of that file. And DOS simply means kernel oops, like cause the kernel to hang or the application to stop. And information disclosure means the kernel may leak some potentially sensitive data to some untrusted party. And examples are like copying a random crypto key from kernel stack to the user space. Okay, there are 3 observations from this table. The first is that we see that buffer overflow and integer overflows are the top threats to the kernel's integrity. There are in all 25 of them out of the 32 vulnerabilities that might cause memory corruption. Second, we found that DOS attacks is the most common type of impacts. There are 60 of them, and nearly half of all the vulnerabilities we have studied. And third, we found that there are many bugs that could lead to a violation of high-level security policies. And we call these bugs semantic bugs, and we'll talk about that later. We also studied the distribution of vulnerabilities in the kernel code base. Here, the reply core means the code that must be statically linked into the kernel image, and the rests are loadable modules, like device drivers, network protocols, and file systems. The observation from this figure is that we found that vulnerabilities are actually evenly distributed in all parts of the kernel. Therefore, a technique that just targets on only one of them is of limited use. There's no vulnerability that is more important than the other. Okay. Like for example, some tools that maybe trust the core kernel and try to isolate modules from the core kernel, and this tool then cannot address the 1/3 of bugs that lies in the core kernel. And some tools that just focus on device drivers or file system, then these tools only address 1/5 of all the vulnerabilities at their best. Okay, so now let's look some existing tools that try to prevent these vulnerabilities. We studied both runtime tools that try to prevent these bugs like BGI, and also some static analysis tools like Smash that try to pinpoint vulnerabilities. This table summarizes the effectiveness of the existing tools. The middle row shows the number of vulnerabilities each tool prevented. And the third here, we see that we count the number here only if we believe this tool can solve all kinds of exploits that try to take advantage of that vulnerability. Therefore, the numbers are so small here. And the third row means the limitation of these tools. That is why the tool cannot prevent the rest of the vulnerabilities. So here are two conclusions we draw from the result. First, we found that solutions that focus on one part of the kernel are insufficient, and we have talked about that. And the second is tools that focus on certain classes of exploits are of limited use. For example, we know that BGI is a short-well fault isolation tools. So the BGI is only work for loadable modules and only workable for some attacks that try to cross the protection boundary of that tool. So in all, we found that it can only prevent 15 out of the 141 vulnerabilities we studied. And there are some for static tools like Smash. We don't have the number of vulnerabilities that they could prevent because these tools are not defensive and they try to find out the bugs that could be fixed by the developer. So in theory, they could be solved all the attacks that target that one vulnerability. But in practice, the problem with these tools is that precise and static analysis is hard to scale to the Linux kernel, which have millions lines of code and is written in an unsafe language. So it's hard. It turns out quite hard to make a trade-off between false positive, false negative, and the scalability. So finally, we found that none of the above tools actually address two bugs. They are semantic vulnerabilities and DOS attacks, and we think they are challenging and could be interesting problems for future research. Now let's look at the semantic vulnerabilities first. What are semantic vulnerabilities? We can say that they are violations of some high-level security policies. For example, the VFS layer in Linux, it assumes that only the owner of the file could change the permission. But the file system driver that implement this interface may forget to perform the check or do the check in the wrong way. Then we have a security hole and the attacker could take advantage of this vulnerability.